Today we walk through some of the most important experiments that have changed the way we think about stuff. By stuff, I mean matter, of course. One of the earliest recorded theories of matter comes from Aristotle, who believed that all matter was made up of 4 elements, 3 of which you can see here, earth, wind, and fire. And, of course, if you're a Ch2 fan, the last element is water, represented by Big Mike as rain. Anyone? As popular as the 4th element theory is in popular mythology, none of that theory is borne out by modern scientific experimentation. So we have our first example of how science works in action. Aristotle made a theory based on observations, and literally everyone who has actually performed experiments since then has proven him wrong. To celebrate this, he gets a band name in his theory's honor. A French chemist, Joseph Proust, used Lavoisier's conservation of matter to make an important realization in the late 1700s. Whenever materials combine to make the same product, they always combine in the same ratio. This means that we use the same amount of materials to make the same amount of product. This probably doesn't come too much of a surprise to you, since all of modern science is established based on this understanding. But it was revolutionary at the time because it solidified thinking about substances as discrete ratios of materials rather than some mysterious continuum of properties. Modern atomic theory was proposed in the late 1800s by John Dalton, famously colorblind chemist and meteorologist, also of Dalton's law of partial pressure fame, we'll talk about in Chapter 8. Modern atomic theory has 5 basic ideas. First, Dalton hypothesized that there was some basic unit of matter. Proust's law of constant consumption seemed to indicate this already, and it wasn't actually a new idea anyway. It was theorized with no evidence by Greek philosophers over 2,000 years before. The second piece is that an element only has one type of element, and all atoms will have the same mass. This is actually the only part of Dalton's law that is a little off. Isotopes, which we'll talk about later, mean that not all samples of an element have the exact same mass, but most samples of the same element have the same average mass. Third, elements are different from one another. Even the alchemists knew elements were different from each other. They just had the wrong elements. Earth, wind, and fire instead of, gold, mercury, lead. Fourth, compounds exist where elements are combined. This is just an interpretation of Proust's data in terms of some elementary particle. And finally, atoms are never created or destroyed. They're just rearranged. This is again just repackaging Lavoisier's observations in terms of atoms too. Lavoisier said we conserve matter, Dalton says we conserve atoms. But it allows us to think about these ratios based on some unitary, an atom, rather than mass, which is one of the most substantial early implications of this theory. From this, Dalton, and others like Thomas Thomson, were able to establish relative atomic weights. Interestingly, the 4th and 5th assertions seem to be the main reasons Dalton proposed discrete elementary units, as he sought to establish another theory, a law of definite proportions. This law of multiple proportions is based on the multiple products that can be formed from 2 identical reactants. Much of Dalton's early work was centered around oxidation and combustion, and Dalton had noticed that carbon could oxidize partially with a small amount of oxygen to a compound we now call carbon monoxide, or it could also oxidize fully to a compound called carbon dioxide. That's interesting in and of itself, but Dalton found that it was even more interesting that the ratios of the amounts of oxygens consumed were 2 to 1, twice as much in carbon dioxide as in carbon monoxide. And the ratios from Joseph Proust's early data were also small whole number ratios. Here's an example from your text that shows how it would work with 2 copper chloride compounds that are very visibly different, although ironically perhaps not to colorblind Dalton. If 1.000 grams of copper is reacted with 0.558 grams of chlorine, a green compound forms. If you take the same starting amount of copper and react it with twice as much chlorine, 1.116 grams of chlorine, a completely different compound forms, which can be characterized by different physical and chemical properties. But if you take the ratio of these 2 amounts relative to the amount of chlorine, it's 2 to 1. Dalton theorized first only that this meant that the ratios would always be small whole numbers. This was certainly true of the inorganic compounds known at the time, although it isn't actually true of many organic molecules. As indicated before, this observation probably was central to Dalton's atomic theory that posited atoms combine in discrete ratios. And this observation, along with atomic theory, form the basis for molecular formulas. We've done a lot of name dropping, not so much that it ultimately matters who did what, but to show you that science is done best when it's collaborative. We named at least 4 contemporaries that were publishing and reading each other's experiments, which led to a rapid expansion of the understanding of chemistry, although there are dozens more working at the same time along the same lines. This collaborativity is an essential good to science, and it's the open sharing of data that led to some of the initial misconceptions of atomic theory to be corrected quickly. So hopefully, we can not only see some of the most important fundamentals of modern chemistry, but also how they demonstrate science done well. Theories don't typically emerge perfectly, but, to speak chemically, iron sharpens iron, and more precise understandings of the world around us are constantly being developed. At risk of digression, as I always am, I'd also like to point out that atomic theory was mostly right even 200 years ago. The minor corrections since then are illustrations that science works, not an illustration that science is flawed. As people began to accept the possibility of the existence of atoms, scientists began to theorize about what an atom actually is. One of the earliest hypotheses by William Prout was that since all of the known atomic weights were roughly multiples of hydrogen's atomic weight, all elements were made up of hydrogen. He called this essential substance protyle, which, spoiler, you may recognize as being very similar to the word proton. Thomas Thomson, who was one of the first to realize how important this atomic theory was, published this idea of protyle in a text that his medical students were to use at the University of Glasgow. He had all his students round atomic weights to make clear that they were multiple of hydrogen based on the theory of protyle. The first actual information about atomic structure was discovered, though, by J.J. Thomson, who, to my knowledge, is in no close relation of Thomas Thomson. Apparently, Thomson's just a popular name for physicists. J.J. Thomson, shown here, was a physicist who studied, taught, and researched at Trinity College in Cambridge, and developed an apparatus known as the cathode ray tube. While this technology eventually became the foundations of the first televisions, it was far more important in helping us to understand electrons. It works like this: a glass tube that has almost all the gas pumped out of it and has a potential difference, a voltage, applied across 2 electrodes. The cathode, which by convention is negatively charged, is separated from the anode, which is positively charged. The anode has a slit in it. Because small amounts of gas are still present, they can be excited and charged to complete a circuit between the cathode and the anode. Some of these charged particles continue on past the anode as a visible cathode ray. An electric or magnetic potential can be applied to the cathode ray, forcing it to bend. Turns out the cathode ray always bends towards the positive surfaces. Again, positivity is assigned by convention, not by any sort of deeper truth about what charge is more important or whether one is actually positive or negative. From this experiment, Thomson was able to assert that cathode ray particles, which we now know as electrons, are negatively charged. Because they occurred no matter which gas was left in the cathode ray tube, Thomson asserted that they were a fundamental part of all atoms. In the experiments with a magnet, the mass-to-charge ratio for these particles was also calculated. A charge-to-mass ratio is great, but it is even better if you can know the charge to begin with, because then you can have a mass too. Robert Millikan performed an experiment to show just that. The basic idea is this: since X-rays are ionizing radiation, they can be used to ionize particles. This was known at the time. Millikan used oil droplets because they don't evaporate readily. When they are sprayed into a chamber, some fall through a pinhole, governed by gravity. This can be counteracted by applying a negative charge below the particles, suspending them mid-air. It's pretty neat. I think modern physics does this experiment with Dr. Chen. The potential required to suspend the droplets of oil can change, but it's always going to be a multiple of 1.6 times 10 to the negative 19th coulombs, which suggested that, while multiple electrons may be removed in some particles, they all had the exact same charge. So 1.6 times 10 to the 19th coulomb, 10 to the negative 19th coulombs was the charge of an electron. So people started to quickly accept that atoms aren't actually indivisible, but are made up of simpler particles, including these electrons. People also widely knew that atoms were neutral, so that the positive had to be in there someplace to balance out the negative. Thomson, J.J. that is, proposed that atoms look like plum pudding. Think raisin bread if you're not British. Electrons would be the raisins, and the bread would be the positive charge. This model is widely taught as part of the development of atomic theory. Hantaro Nagoka proposed a less-known Saturn model where electrons orbit closely around a positive charge center. But how can we tell which is actually true? Well, with experiments, of course. Ernest Rutherford, as well as Hans Geiger of Geiger counter fame and Ernest Marsden, shot radiation at a thin gold foil. The alpha particles in the beam were known to be positively charged. You would expect different deflection patterns coming off of the gold foil depending on the model. The plum pudding model, being evenly dispersed, should deflect positively charged particles relatively evenly, but around the back half of the deflecting screen. The Saturn model would also mostly deflect alpha particles, but depending on the orientation of the rings, perhaps less uniformly. What Rutherford and colleagues found was actually kind of surprising. It didn't support either model since most of the alpha particles passed straight through. So, since both models at the time would have given different results in the gold foil experiment, they're both incorrect. Rutherford instead proposed a model more similar to the Saturn model, but where Saturn is really tiny compared to its rings. Here's what Rutherford actually theorized. Atoms are mostly empty space. Otherwise, the alpha particles would have been deflected more. A small, positively charged nucleus centers the atom. Since some deflection happens, there has to be a positively charged part, but since it's not much, it has to be small. And symmetry would allow atoms to not carry a charge gradient or a dipole, which isn't observed. Rutherford continued to work with alpha particles and found that alpha particles could release hydrogen atoms from other elements, suggesting Prout's hypothesis about hydrogen atoms being fundamental building blocks of all elements was actually correct. Based on Prout's protyle name for this substance, the hydrogen nucleus became known as a proton. Rutherford's model is starting to look very similar to our modern model, but it isn't quite there. Chemists began to isolate strange products from nuclear decay. They had different atomic masses than other elements, but they actually had the same chemical properties as existing elements, suggesting that they were actually the same element. English chemist Frederick Soddy suggested that the element might have multiple types of atoms that had different masses, which we now call isotopes. The Nobel Committee and many other chemists thought it was a great idea. For a while, people assumed the extra mass was from protons, along with nuclear electrons, but that leads to all sorts of problems with actual data. Walter Bothy and Herbert Becker performed a similar experiment to Rutherford's alpha particle bombardment experiment that showed if you bombard certain types of elements with alpha particles, radiation with greater penetrating power than hydrogen atoms was formed, so something that was either less charged or less massive was being formed. This was originally thought to be gamma radiation, but the following year, Irene Joliot-Curie and Frédéric Joliot-Curie showed that it could liberate hydrogens from large organic compounds called paraffins, think wax, and calculated the necessary values of energy in the radiation if it actually was gamma rays. This is one of the clearest ways to test a theory. If the theory is true, it will have some effect on the observable phenomenon, and the Curies were able to predict what that would look like. James Chadwick, Rutherford's student and assistant director of research, saw the Curie's data and immediately performed experiments to show that other ionizations by the same type of radiation could not be explained by gamma rays, but could be explained by a neutron. People had been looking for an explanation for the extra mass for over 7 years, and with the right exposure to current research and about 2 weeks of actual research, the world had a much better understanding of the atom that propelled us into the nuclear age, and Chadwick had the makings of a Nobel Prize. Based on this, Werner Heisenberg, also already a Nobel laureate for modeling electron dynamics using perturbations to solve models and matrix methods, released a modern proton-neutron model of the nucleus, a nucleus that had both protons and neutrons.